is.
Oh, we don't have this problem again.
No, no.
Oh, I'm just good. Oh, great. All right, yeah, so assignments, please bring them up. How about, yeah, right here would be fine. Okay, so while you're doing that, I'll just make the standard announcement. So assignment 6, I'll post this weekend. I don't know what the due date will be, but it won't be next week, so don't worry about that. And then yeah, formal reports, just make some progress on your formal reports so that you're not trying to scramble to get it done in the last couple of days.
That's a quick question.
Yep.
The like error analysis factor that comes
Yep.
in the grading.
Yeah.
Do we have to like show our error propagation, or is it really just having a number, like having a?
Yeah, I mean, I think like in first year, what you end up doing is you end up probably like doing example calculations and stuff like that. I don't need to see that. Like what I would do is I would explain when you're estimating errors in measured quantities, explain how you made those estimates. And then when you're calculating the uncertainty in a calculated value, I would probably just say that we used propagation of errors. And
Okay.
like maybe in your report, you give the general equation for propagation of errors once, and then you could just say, we use this to calculate whatever the uncertainty and Planck's constant.
Sounds good.
Yeah, yeah. Any other questions about formal report stuff? All right, so we kind of finished up one of our big topics last time, and that topic was what we're trying to do is analyze some data, do a fit to determine some parameters A1, A2 up to AM that follow this form y of x is A1 times some function of x plus A2 times another function of x and so on. And the only restriction was that these functions of f1, f2, sorry, functions of x, f1, f2, up to fm, they just can't involve the parameters that we're trying to find. Other than that, there's no restrictions. So we imagine, as usual, we made a set of measurements and we want to find these values. We ended up constructing a matrix, and we could calculate the elements of epsilon was the inverse of alpha. We could calculate all the elements of alpha and beta just from our measured values, xi and yi plus or minus sigma I. Then we end up inverting alpha to get this epsilon. And then this calculation just gives us a list of all of our best fit parameters. And one of the great things about this was that epsilon matrix also tells us the uncertainties in our parameters. So it tells us the square of the uncertainty. So the diagonal elements, if you take the square roots of them, give you the uncertainties in all your best fit parameters. Okay, now what we need to do is we need to go on and consider the last type of fit. If I can find my notes, here we go. Oh crap. Hang on. Got a page torn off. Nonlinear fits. All right. So what we're going to do is we're going to start by showing why the type of analysis that we did for linear fits and this last example, why that breaks down when we try to consider a non-linear function. So let's examine the case of a non-linear fit. And we'll do this by selecting a specific example. So what we're going to have is y of x is not of the form ak times fk of x. All right. So what we'll do is we'll make ourselves a table. So the example that we'll consider is y of x is going to be equal to a1 times sine a2 times x. So that's a nonlinear function. If this was just a1 times sine of x, then we could use this method, right? We could just say f1 is just sine of x. It doesn't involve any a's, and so we just use the method that we had before. But if we have an a2 inside here, I can't express this in this form. And so this is a nonlinear function. It's a pretty simple one, right? It's just a trig function. But I'm going to show, I hope, that even this simple example of a nonlinear function cannot be analyzed in the way that we've been doing for our other examples. Okay, so let's compare and contrast linear and non-linear fits. Okay, so I'll start a table. I'm going to start a fresh page, and so we'll just divide this thing in half. So the first thing we'll do is we'll do our linear case on the left, and we'll do our non-linear case on the right. So for the linear case, we'll just use a simple example. Y is a1 plus a2 times x. So just a straight line. And then over here, we'll do our y is a1 times sine of a2x. Okay, so in both cases, the objective will be to minimize chi-squared. So chi-squared was equal to the sum of I equals 1 to n of our y measurements minus y calculated at the x value divided by sigma, the uncertainty in y, I, and then we square it and then sum them up. And so our objective was to try to minimize this chi-squared function. If I substitute in our function of y right here, what our chi-squared ends up looking like is chi-squared is the sum of I equals 1 to n yi minus. It would be a1 minus a2 xi divided by sigma I squared. Okay, so let's start filling in the other side. If we want to kind of treat the nonlinear case in the same way, we would say, okay, chi squared has the exact same definition. So I'm just going to rewrite this thing. The only thing that's different is the form of y of xi. And so when we substitute that in, we get chi squared is equal to sum of I equals 1 to n of, let's see, yi minus a1 sine a2 xi divided by sigma I squared. All right. So those are our chi-squareds, and we're going to try, the goal is to try to adjust the parameters a1 and a2 so that when we do this calculation, when we do the sum, we get the minimum possible value. Remember, we wanted a minimum chi-squared just because we had this like e to the minus chi squared was our probability, and we're doing this method of maximum likelihood. So if we minimize chi squared, we maximize that probability. So the way we do the minimization is we have to evaluate these derivatives with respect to the parameters. If we do the A1 derivative here, factor of 2 comes down. So we would have, let's see, 2 times the sum of, let's see, yi minus A1 minus A2 xi divided by sigma I. And then we have to, so that's brings down the 2, and then we get that. And then we have to take the derivative of what's inside with respect to A1, and we'll get a minus 1 over sigma I. So we have to multiply all of this by minus 1 over sigma I. Okay, so fair enough. And then that has to be equal to 0. And what that allowed us to do is to write that the sum of, let's see, yi over sigma I squared. So we could divide by 2, and then 0 divided by 2 is still 0. So I'll get rid of the 2. Then we have yi sigma I, so that's yi over sigma I squared. There's a minus sign, and so we'll take this over to the other side of the expression. And we would say that would have to be equal to, let's see, the sum of A1 plus A2 xi over sigma I squared, I think. Yeah. So the minus sign kills these minus signs, and then we just have this A1 plus A2 xi divided by sigma I, and then divided by sigma I again. So it becomes squared here. Okay, good. So I'm going to call this equation 1. And then what we're going to try to do is we're going to try to do something like that for the nonlinear fit. So we have to do this derivative with respect to A1. So it starts the same. We get a 2 times the sum of yi minus A1 sine A2 xi divided by sigma I. And then we have to take the derivative of what's inside. And here's where we get our first bit of problem. We're going to get minus sine of A2 xi divided by sigma I. So we have to multiply all of this by minus. So sine A2 xi over sigma I. And then that has to be equal to 0.
Are you taking the derivative with?
But I'm taking the derivative with respect to A1.
Yeah.
We are going to do the A2 one, and we will get a cos when we do that. Yeah, but that's coming. Okay. All right. If we try to do the sort of rearrangement that we did over here, where we take the yi to the other side, we can still do that. And let's see, we divide by the 2, so I don't care about that. We're going to end up with, let's see, yi sine a2xi over sigma I squared is equal to, and there's a sum here, the sum of, what's all the stuff that's left over? We're going to get a1 sine squared a2 xi over sigma I squared. Is that right? Yeah, it looks like it. Okay. If we compare these two, I'm going to call this equation, we'll call it, say, 1 prime. If we compare these two, on the right-hand side, we have a sum that involves both of the unknown parameters. And so that's similar in the two cases. What's different is on the left-hand side of the linear fit, we don't have any of the A parameters, whereas here we do have one of our fit parameters, multiplying the yi. And so the first thing we'll observe is that this has no a1 or a2, whereas this involves a2. Okay. All right, well, let's just keep going, and we'll have to do now the derivative with respect to a2. And so I need the original chi-squared, there it is. So it starts the same, we get 2 times the sum of yi minus a1 minus a2 xi over sigma I. And then we take the a2 derivative. This time we get a minus xi over sigma I. So minus xi over sigma I. And that has to be equal to 0. Okay, and then if we rearrange, we're going to get the sum of xi yi divided by sigma I squared is equal to the sum of, well, how did I write it? Yeah, okay. So it's xi over sigma I squared times a1 plus a2 xi. And this is equation 2, I think. And again, when we look at this on the left, we have no a1 or a2. Yeah.
In the one that you had says involves a2, why would you not just divide by sine a2 xi also?
You can't do that, it's inside a sum. You can't do like if I have the sum of, I don't know, x times sine xi or something like that. Let's say yi times the sine of xi. I can't divide by sine of xi and say that's the sum of yi, right? That doesn't work. It's because this is like n different terms, so that's the reason. Yeah. Okay, good. So let's do the same thing for the nonlinear case, and this one's going to be even worse. So we go the derivative of chi-squared with respect to a2. Sorry, a2 is equal to, so we get the 2 yi minus a1 sine a2 xi divided by sigma I. And then we have to multiply by, okay, so the a2 derivative, what's that going to do? It's going to bring out a factor of xi. So we're going to have an xi, it's going to multiply the a1. We still have a 1 over sigma I. The sine becomes a cos. And then we have a2 xi. And then I think we still have a minus sign. There we go, and then that has to be equal to 0. Okay, let's see, did I get that right? I think so. Okay, if we do a rearrangement here, we would end up with, let's see. We're gonna get xi, yi. So xi, yi, there's gonna be a sigma I squared. And now we have a1 cos a2 xi. So a1 cos a2 xi, I think. Okay, and that has to be equal to, let's see, it's going to be equal to a bit of a mess. So we're going to have the minus signs cancel. We'll have 1 over sigma I squared. We'll get xi a1 squared, I think. So it's going to be xi a1 squared over sigma I squared. And then we're going to get sine times cos. So cos a2 xi sine a2 xi. What a mess. Okay, but I think that's what it is. And so this will be equation 2 prime. And what I want to highlight is that on the left-hand side, we have a1 and a2. Okay. What we were able to do with the linear fits is we were able to express equations 1 and 2 as a matrix equation. And that made life easy. So for the linear fits, we can express 1 and 2 as a matrix equation with the a k parameters in a single column matrix. And I'll write down what that matrix equation was. It looked like, so the sum of yi over sigma I squared, sum of xi yi over sigma I squared, and that was equal to a matrix over here, and then we had a1 and a2, and this was the sum of 1 over sigma I squared. This was xi over sigma I squared. This one was also xi over sigma I squared, and this was the sum of xi squared over sigma I squared. Okay, and so what we could do is I've got equation 2 on the screen here. And so if we were to do this times this, so we would have xi over sigma I squared a1. And so that's xi over sigma I squared a1. And then we would do, let's see, this times this. We'd get a2 xi squared sigma I squared. And so we'd have a2 xi squared over sigma I squared. And so we can confirm that that second multiplication gives the second equation. The first multiplication would give the first equation. And obviously, we would invert the square matrix, multiply over here, and then we would isolate for our unknown parameters. For our nonlinear fit, we have no hope of representing equations 1 prime and 2 prime as a matrix equation where one of the matrices is a column of the unknown parameters. It's just a disaster, right? We have our parameters stuck inside trig functions. We have a's on both sides of the equation. It's a disaster, okay? Okay, so if this is alpha and this is A, and this we call beta, then we got that A was equal to alpha inverse times beta. So for our nonlinear fit, the AKs and 1 prime and 2 prime are on both sides of the equations, and they're also, and A2 is inside trig functions. We cannot write down an equivalent okay, so we cannot write down an equivalent matrix equation for this case. And so what we need is we need a new fitting method. And it turns out that the fitting method that we're going to develop it's actually a lot less technical than what we've done for the previous 2 cases. So in that sense, it's a bit easier to understand, but it's also less elegant, as you'll see. Okay. So one method for nonlinear fits. So the objective is still to minimize chi-squared. So chi-squared is the yi minus y of xi over sigma I all squared. Okay, so for our example of the sine function, we want to minimize, chi-squared is equal to the sum I equals 1 to n of yi minus a1 sine a2 xi over sigma I all squared. All right. Can anyone think of, if I want to find where chi-squared is a minimum, like what's the simplest, kind of most straightforward, don't have to think hard method of doing that?
Let's take its derivative.
Well, we just did that. We just took its derivative and it was a disaster. Yeah.
Would it be where sine is at a maximum?
Well, not necessarily, because what we're interested in is the difference between our measured y value and our calculated y value.
It's very large. Compared to
Well, that would be a bad experiment, wouldn't it? You have huge uncertainty. So what if you, like, if you wanted to, what do you do if you have, like, you know, these transcendental equations where you have left-hand side equals right-hand side, but you can't solve for a particular variable? So what do you do to find the value that matches that right-hand side? Right, if I wanted to solve, this is, you don't need to write this. If I wanted to solve x equals, I don't know, sine 2x or something, or x squared, like, how would you, what would you do if you wanted to find the value of x like this?
try numerical methods.
Yeah, so what kind of numerical method?
It's a guess number.
Yeah, right, you could just guess some values, right? you could just say, all right, I got a calculator, I'm just gonna put in different values of X until I find that, a solution that's pretty close.
When both sides equal or get close enough.
Yeah, so then you just have to have some criteria for when you're satisfied that, you've got enough accuracy. So we could do something similar for this thing. We're not solving a transcendental equation, but what we could do is we could just take a bunch of A1 values, we could take a bunch of A2 values, and then we're going to calculate pi squared at every possible combination of A1 and A2 values. So if you had like 10 values for A1 and 10 values for A2, you would calculate pi squared 100 times and find the combination of A1 and A2 that gives the smallest value for chi squared. Okay, so strategy 1. We just pick a range. Pick a range of possible values for A1 and A2. So we would have something like A1 minimum, and we'd have what we would consider an A1 maximum. And so we're going to pick some values for A1 that lie between the minimum and maximum. And we do the same thing for A2.
So it's squeezed through.
Yeah, I mean, I think we're not really doing anything even that sophisticated. We're just going to plug some numbers in and find where chi squared is as small as possible. Now there's a subtlety to this, like it wouldn't make sense just to randomly pick minimum and maximum values for our parameter ranges. We would have to know something about our system in order to decide like what are reasonable estimates of these parameters. Like I don't need to test unreasonable values. I want to kind of have some idea of what the value should be and then pick ranges that kind of include those reasonable values. So what we have to do is we have to know something about our physical system to select reasonable ranges for the parameters. And let me just do an example. So example, my favorite example is always the LRC circuit. LRC circuit. So let's see, how did I write it down? Yeah. So for the voltage across a resistor and so L C R. The expression is something like voltage across the resistor is some amplitude divided by let's see, 1 plus omega squared. One way to write it is omega squared over gamma squared 1 minus omega naught squared over omega squared all squared, right? So this is some complicated nonlinear function. It has parameters a, gamma, and omega naught. So we're going to measure VR versus omega, and our fit parameters are a gamma, and omega naught. Okay, and so when you plot the actual data that you're trying to fit, oh, you're early today. We would end up with some data that, I don't know what it looks like. It looks something like this, right? And so imagine these are all like little error bars on here and so on. And so we're going to try to fit this to some kind of function that goes through the data. And if we were going to do the sort of fitting method that we're describing, we would try to select ranges for these various parameters. So in order to do that, we have to know something about the physical system. What does A represent in this diagram? Yeah, the amplitude, which is just the height of the plot, right? So A is going to sit something like, oh, that should be a horizontal line. So A, oh. A is sitting somewhere around here. So what you would do is you'd look at your data, you would find the peak and say, oh, okay, that's my estimate of A. Maybe this is something like, I don't know, 6.28 volts or something. And then you're gonna pick a range of A values that go from, say, 6 to 7 or something like that. I think that would be a reasonable range. What does omega naught represent? It's the resonant frequency, yeah. It is an angular frequency, but it's specifically the resonance frequency. And so you would just go and you would find what frequency does the peak of your data occur at. And so, you know, maybe it's, I don't know, 12.6 kilohertz. And then you say, okay, I'm going to pick a range for omega naught that goes from 12 to 13 kilohertz. And then gamma represents how wide this distribution is. And so this is gamma is something like this. So you go to A over root 2, and you see how wide the thing is. And so that's a width in a certain number of kilohertz. And then again, from your data, you select a value of gamma that's reasonable, right? You're not going in blind. You're going in with some idea of what the parameters are likely to be. Okay. So anyways, the whole point of this was to use the measured data to estimate what the fit parameters are likely to be. Okay. So now we've done step one. We've looked at the data that we've measured, and we've selected some ranges for some possible ranges for our fit parameters. In the example that we're doing, there's two fit parameters, A1 and A2. In the example of the LRC circuit, we had 3 different fit parameters. Okay, so step 2 is to pick a step size, say delta A1 and delta A2 for each parameter. So we're going to go from, say, A1 minimum, and then the next value in our range will be A1 minimum plus delta A1, and the next value would be A1 minimum plus 2 delta A1, and you continue like this until you get to A1 maximum. So of course, picking a small step size is going to give you a lot of resolution in determining your fit parameters, and usually that's the best thing to do, because especially in software, like we're probably not going to sit here and calculate 100 chi-squared values by hand, we'll write up some code in Python or do it in Excel or whatever you want to do all these calculations for us. And they do them almost instantaneously. So you don't have to hesitate about picking a small step size. Okay, so a small delta A1 and delta A2 is good for a high resolution, but takes longer to calculate all chi-squared values. But like I said, unless you're doing like millions and millions of values in software, this will be really fast. Okay. So step 3 is now we have our range, we have our step size, and we just calculate chi-squared for all possible combinations of A1 and A2. So we evaluate chi-squared at all possible combinations of A1 and A2. And the best fit parameters are the values that minimize chi-squared or give the smallest result for chi-squared. One way to represent this kind of procedure is by making a surface plot. And so this works well for 2 fit parameters, but the idea is similar for bigger sets of parameters. So I'm going to challenge my ability to draw here. So let's see how it goes. So I'm going to draw a coordinate system that has an A2 axis and an A1 axis and a chi-squared axis. Okay, and so this continues on. So, all right, and so what we're going to do is we're going to plot all of the values of chi-squared as a function of all of the A1, A2 parameter values. And the result is going to be some kind of surface. And let's see if I can draw this surface well enough. So here's kind of roughly a plane. And what we're looking for is where does our surface reach a minimum? So it's not looking too bad. I think I can make it slightly better. Let's draw like a well-defined minimum. Okay, and I'll draw some, supposed to represent some curvature in here. And so here's some curve. So it's like this little bowl here. And down here somewhere is the minimum possible chi-squared. And so this would be, how am I going to draw that? Something like this. So right here is going to be well, okay. We'll just draw a straight line to chi-squared. So this would be chi-squared minimum would sit here, and then this would project down to somewhere in our plane of A1 and A2 values. Okay, so that's the projection down here. And this I'll call A2 star, and I'll call A1 star. And so that's the particular combination that led to the smallest possible value for chi-squared. Okay, and then this dashed line, ooh, I can draw this a little bit better now. If I make this one parallel to the line in the plane, then chi-squared minimum sits over here. I don't know, is that picture clear enough? Does it make sense? Any questions about that? Chi-squared sits here. All right, so obviously, if I had like 3 parameters, I couldn't like sketch this picture by hand. But in principle, the idea is the same thing. You're just going to calculate all the possible chi-squared values for all combinations of A1, A2, and A3. Whichever combination gives the smallest number for chi-squared is your estimate of the fit parameters. Okay, so if A1 star, A2 star give the minimum value of chi-squared, then they are our estimates of the best fit parameters. The other thing I was going to say is that you have to be a little bit careful with this type of analysis, because what you can end up with is, for really complicated functions, like our example of A1 times sine A2x is pretty simple. But you could imagine you could have very complex nonlinear functions, and the surface that you get here may not have just one big minimum. It may have a whole bunch of local minima and one maximum minimum that you're looking for. So if the non-linear,
That's gonna depend on our initial guesses.
Yeah.
For that.
that's right, if the nonlinear function is very complicated,
Would those also be the start values for our Python fits?
the what?
The start values that we put in.
Oh, yeah, the start value. So yeah, you're putting in initial guesses for what those parameters are. So Python does some of the work for you, right? When you go into Python, you're just giving some starting values. You're not selecting a whole range of values. Python's going to pick the range for you. But they're going to do it in a smarter way than we are. Like they'll probably do like some kind of gradient search. So they'll start at your start value, they'll evaluate the gradient, and they will change the parameter value following the steepest descent in the chi-squared value. And they have to do that simultaneously for all of the fit parameters. We might talk about that briefly, but maybe not in too much detail. So if the chi-squared, or if the nonlinear function is very complicated, the chi-squared surface can have local and global minima. You can get trapped in a local minimum and miss the global minimum. So in 1D, I can't draw that in more than 1D, but if you had a best fit parameter and chi-squared, and if your plot looked like this, what might happen is you might start doing a search right here where you say, okay, this is going to be A1 minimum, and this is going to be A2 maximum, and you do your grid search, and then you identify this, sorry, I don't if this is just 1D, so I don't need A1, A2, sorry, this is just a minimum. This is a maximum, and then you might identify this as a star, your best fit value, where you have a small value of chi-squared. But of course, that means that you haven't had a large enough range to scan through. And so this is chi-squared local minimum. And this is chi-squared global minimum. And if you're not careful, you can miss that global minimum where the best fit parameter sits outside your range. Or what I won't draw, but what could happen is if you had a really complicated nonlinear function, even inside of your range of values, you could have several minima. And one of them's the global, but if your search is too coarse, you might skip over that global minimum. So there are some pitfalls to this type of method. What we're gonna do next week is we've described, sorry, yeah, go ahead. Oh, this is maybe where you start your search, some starting value. But yeah, you're right, it doesn't need to be there. So we've come up with a procedure that could give some reasonable values for your best fit parameters, but we haven't estimated the uncertainties, and that's what we'll work on next week. Okay, good. Thanks very much. Have a good weekend. If you haven't already, please bring your assignments up, and we'll see you we'll see some of you Tuesday, some of you on Wednesday. Yeah.
When do you want us to, it's the last lab next week, right?
Yeah.
When do you want us to submit our lab report?
It'll be the same thing 1 week later. You just have to, yeah, if you want to, you can bring them to class, or I'll be in the lab. So we'll make the due date Wednesday at 11. Yeah.